Something happens when you look up at the night sky and let a familiar question to settle into your mind. Is anyone out there looking back? Back at the very same stars you see. The stars appear as scattered points of light. Each one is a sun, and many of them hosting worlds we cannot see from this distance. Worlds that might be barren or might hold something remarkable. The question is ancient, older than science itself, asked by every generation of humans who tilted their heads toward the darkness and wondered about their place among those distant lights. Tonight we explore that question together, following a path that scientists created to turn wonder into something we can think about carefully. The first time I encountered this approach to the question, I was struck by its elegant simplicity and its honest admission of how much we do not know about the cosmos. Someone had found a way to break an impossible question into smaller pieces, each piece representing something we might eventually understand, or at least estimate with reasonable guesses. The approach does not give us a final answer, but it gives us a way to think, a framework for organizing our curiosity about civilizations among the stars. That framework has a fascinating origin story involving a small gathering of scientists in the early 1960s. A story we will explore later in our journey tonight. You are listening to The Drowsy Astronaut, and this is a slow, unhurried journey through one of the most profound questions humanity has ever asked. We will move gently through each piece of this puzzle, taking our time, letting the ideas settle, like starlight reaching Earth after traveling for years through empty space. If you feel like sharing where you are listening from tonight, the comments are always open for those quiet notes from around the world. For now, we begin with the question itself, the possibility that we are not alone in this vast galaxy of ours. The Milky Way contains somewhere between 200 billion and 400 billion stars, a number so large that it loses meaning when spoken aloud without some way to feel its scale. If you counted one star per second without stopping, it would take you thousands of years to count them all, and you would need to keep counting through generations of descendants, continuing your work. Each of those stars is a sun, some larger than our own, some smaller, some hotter, some cooler, but each one a furnace of light burning in the darkness between here and there. The galaxy is vast, and the question of whether any of those countless suns warm worlds where someone wonders about us is worth asking carefully. The stars are not evenly distributed, but gathered into spiral arms that curve around the galactic center, dense rivers of suns flowing through the structure of our home galaxy. Our own sun sits in one of these arms, a minor arm called the Orion Arm, positioned about halfway between the galactic center and the outer edge of the disk. From our position, we see the galaxy edge on when we look at the Milky Way stretching across the summer sky. That band of soft light, actually composed of billions of stars too distant to resolve individually with naked eyes. Somewhere in that glow, there might be other minds looking outward, seeing their own version of the Milky Way, wondering about the lights they cannot quite resolve. The question of extraterrestrial intelligence is not merely philosophical, but has become a scientific pursuit, with dedicated researchers, telescopes, and carefully designed search programs operating around the world today. Scientists take the question seriously, not because they know the answer, but because the question is answerable in principle if we know how to look and where to listen. The search has been ongoing for more than 60 years now, listening for signals that might indicate technology, scanning the sky for anything that seems out of place. So far, the sky has remained quiet, but the search has barely scratched the surface of what could be explored, given enough time and resources. When scientists began thinking carefully about this question in the 20th century, they faced a problem that seemed almost paralyzing in its scope and uncertainty. How do you even begin to estimate how many civilizations might exist when you know so little about how life begins, how intelligence evolves, and how long technological societies might survive? The answer came from recognizing that the impossible question could be broken into smaller questions, each one uncertain, but at least approachable with data or reasonable guesses. This breaking apart of the grand question into manageable pieces became the framework that guides thinking about extraterrestrial intelligence to this day. The framework works like a series of filters, starting with all the stars in the galaxy and progressively narrowing down through each condition that must be met for a civilization to exist and be detectable. You begin with the vast number of stars and ask how many of those have planets, then how many of those planets might be suitable for life, then how often life actually begins on suitable worlds, then how often life develops intelligence, then how often intelligent species develop technology, and finally, how long such technological civilizations last. Each step narrows the count, and the final result depends entirely on what numbers you put into each step of the filtering process. The beauty of this approach lies not in the answer it produces, but in the conversation it enables about each separate question along the way. Some of these questions have become much better understood since scientists first began asking them, particularly the astronomical questions about stars and planets that observations have steadily illuminated over recent decades. Other questions remain deeply uncertain, particularly the biological and sociological questions about life, intelligence, and the longevity of civilizations that we have only one example to study. The framework embraces this uncertainty, honestly, showing where our knowledge is solid and where we are mostly guessing based on hope or caution. The first piece of the framework asks about stars themselves. How many new stars form in our galaxy each year, providing fresh suns around which new planetary systems might develop over cosmic time? This is not asking about how many stars exist in total, but about the rate of creation, the ongoing birth of new stars in stellar nurseries scattered throughout the spiral arms. Astronomers have studied star formation extensively and have reasonable estimates for this rate, making it one of the better-known pieces of the puzzle we will explore tonight. New stars mean new opportunities for planetary systems, new chances for the conditions that might eventually lead to life and mind. The next several pieces of the framework continue the astronomical investigation, asking about planets and their properties, questions that have been revolutionized by discoveries in recent decades. When scientists first proposed this framework in the early 1960s, no planets had been detected around other stars, and no one knew whether planetary systems were common or rare throughout the galaxy. The universe might have been full of lonely stars with no worlds to warm, or every star might be surrounded by planetary companions, and there was simply no way to know which reality we inhabited. Today, we know the answer to that question, and it has transformed how we think about the possibilities for life beyond Earth. Following the astronomical questions come the biological ones, asking how often life begins on suitable worlds, and how often that life eventually develops the capacity for thought and curiosity. These questions are harder because we have only one example to study. Our own Earth, with its single origin of life and its single technological species among millions of other species that never developed technology. The sample size of one makes statistical reasoning difficult, and scientists disagree about whether Earth's story represents a common pathway or a lucky accident that might rarely repeat elsewhere. The honest answer is that we do not know, and the framework makes that uncertainty explicit rather than hiding it behind false confidence. The final pieces of the framework ask about technology and time, whether intelligent species develop the means to communicate across interstellar distances, and how long their civilizations remain detectable to others who might be searching. These questions touch on sociology, politics, and the long-term survival of technological societies, subjects far outside traditional astronomy, but essential to estimating whether anyone else is out there trying to make contact. A civilization that destroys itself after a brief technological flowering would be almost impossible to detect, while a civilization that endures for millions of years would have ample time to be noticed across the vastness of space. The number you get at the end of this framework depends entirely on the numbers you put into each step along the way. And different scientists, using different assumptions, have produced estimates ranging from millions of civilizations in our galaxy to the possibility that we are entirely alone. The pessimists argue that one or more of the steps must be extremely improbable, filtering out almost everything and leaving perhaps only us or no one at all. The optimists argue that life and intelligence may be natural consequences of planetary evolution, emerging wherever conditions permit over sufficient time. The truth is that we do not yet know which view is closer to reality. Tonight we will walk through each piece of this framework slowly and carefully, exploring what we know and what we wonder about each step in the chain from stars to civilizations. We will visit stellar nurseries where new suns are born, planetary systems where worlds orbit in the zones where liquid water might exist, and the mysterious transition from chemistry to biology that happened at least once on our own world. We will consider the long history of life on Earth and the relatively recent emergence of minds capable of asking these questions and building machines to extend our senses into the cosmos. The journey will be gentle, taking time with each idea, letting the facts breathe and the questions linger without demanding immediate answers from a universe that keeps its secrets close. Some pieces of the framework are now well understood, illuminated by decades of astronomical observation and discovery, while others remain shrouded in uncertainty that may persist for generations to come. The honest approach to this question is to distinguish clearly between what we know and what we guess, celebrating the knowledge while acknowledging the vast regions of our ignorance that remain to be explored. The stars above are real, the planets around them are increasingly well documented, and the question of whether any of those worlds harbor life or intelligence is worth taking seriously, even if we cannot yet answer it. Scientists continue searching, continue listening, continue building better instruments to extend the reach of their inquiry deeper into the galaxy's billions of star systems. The question is not whether we will eventually learn more, but whether the answer, when it comes, will reveal a universe teeming with life, or a cosmos where Earth's spark of awareness is rare beyond imagining. For now, we have the framework, the approach, the way of thinking that turns the overwhelming question into something that can be discussed one piece at a time. We have the observations that have already filled in some of the blanks with actual data rather than speculation. And we have the honest acknowledgement of where we remain ignorant despite our best efforts. The journey through this framework is a journey through our current understanding of the universe and our place within it. A journey that begins with the stars themselves and the ongoing process of their creation that has continued for billions of years throughout our galaxy and continues tonight while we rest and wonder. The first piece of the framework, the foundation upon which all the other pieces rest, asks about the stars and how they come to be in the first place. Without stars, there are no planets. Without planets, there is no stable environment for life. Without life, there are no minds to wonder and no technology to reach across the emptiness between distant suns. The stars are where it all begins, and understanding their formation is the first step in our slow journey through the question of whether we are alone or one among many civilizations scattered across the vast spiral of the Milky Way. Stars are being born right now, at this very moment, in giant clouds of gas and dust scattered throughout our galaxy, and others beyond counting. The process never stops, has never stopped since the first generation of stars ignited in the young universe billions of years ago, and will continue for billions of years to come until the raw material is exhausted. Somewhere in the darkness between existing stars, gravity is pulling gas together, compressing it, heating it, beginning the slow transformation from cold cloud to blazing sun. This ongoing creation provides the foundation for everything else we will consider tonight. The clouds from which stars form are called molecular clouds, vast regions where hydrogen gas has gathered densely enough to collapse under its own gravitational attraction when conditions are right. These clouds can be enormous, spanning tens or even hundreds of light years across, containing enough material to form thousands of stars if fully converted into stellar objects. The clouds are cold, only a few degrees above absolute zero in their densest cores, and dark, blocking the light of stars behind them to create silhouettes against the brighter background of the galaxy. Within these cold, dark regions, the process of star formation unfolds over millions of years. The trigger that begins collapse can come from many sources, perhaps a nearby supernova sending shockwaves through the cloud, perhaps the passage of a spiral arm compressing the gas as the galaxy rotates. Once collapse begins in a region of the cloud, gravity takes over, pulling more and more material toward the center of the collapsing pocket, heating it through compression as the gas falls inward. The center grows hotter and denser over hundreds of thousands of years, eventually reaching temperatures and pressures where hydrogen atoms begin fusing into helium, releasing energy that marks the birth of a new star. The newborn star pushes back against further collapse with the energy of its nuclear fusion, reaching a balance between gravity pulling inward and radiation pushing outward that will persist for millions or billions of years, depending on the star's mass. Larger stars burn hotter and faster, consuming their fuel in mere millions of years before dying in spectacular explosions that scatter heavy elements back into space for future generations of stars. Smaller stars burn cooler and slower, potentially lasting for trillions of years, far longer than the current age of the universe, patient and steady in their glow. Our galaxy produces roughly 1 to 3 new stars per year when measured in terms of total stellar mass being created across all its star-forming regions combined. This might sound like a slow rate, but it has been continuing for more than 10 billion years, adding up to the hundreds of billions of stars that now populate the Milky Way. The rate was higher in the past when more raw material was available, and it will gradually decrease in the future as the galaxy's gas reserves are converted into stars or expelled by stellar winds and explosions. For now, the process continues, refreshing the stellar population with new suns that might host new worlds. The most active star-forming regions in our galaxy are found in the spiral arms, where gas tends to pile up as it orbits the galactic center at slightly different speeds than the spiral pattern itself. The Orion Nebula, visible as a fuzzy patch in the sword of the constellation Orion, is one of the closest active star-forming regions to Earth, only about 1,300 light-years away. Within that glowing cloud, new stars are being born right now, surrounded by disks of gas and dust that may eventually form into planetary systems orbiting those infant suns. The nebula glows with the light of its youngest, hottest stars, illuminating the gas from which they recently formed. Other famous star-forming regions include the Carina Nebula, host to some of the most massive and luminous stars known anywhere in our galaxy, and the Eagle Nebula, with its iconic pillars of creation, photographed by the Hubble Space Telescope. These regions are violent places by astronomical standards, with intense radiation and powerful stellar winds, reshaping the clouds even as new stars continue to form within them. The beauty visible in the photographs masks an energetic environment that would be hostile to any life as we know it. Though the stars being born there may eventually host calmer planetary systems after they drift away from the nursery. Not all stars are equal when it comes to the question of hosting life, and the diversity of stellar types affects how we think about the possibilities for civilizations elsewhere in the galaxy. Massive stars burn so hot and die so quickly that there would be little time for life to develop on any planets orbiting them. Their brief lives of a few million years, too short for the slow processes of biological evolution. Smaller red dwarf stars are far more common, making up perhaps 70% of all stars in the galaxy. And they live for incredibly long times, providing stable environments for potentially trillions of years. Red dwarf stars have their own challenges for habitability, including flare activity that could strip atmospheres from nearby planets, and tidal locking that might leave one side of a planet in permanent day, while the other remains in permanent night. Whether planets around these long-lived small stars can support life remains an open question that scientists are actively investigating through observations of real planetary systems around red dwarfs in our galactic neighborhood. The answer matters enormously for estimates of how many potentially life-bearing worlds exist, since red dwarfs are so much more numerous than stars like our Sun. Sun-like stars, called G-type stars in the classification system astronomers use, represent a middle ground between the extremes of massive short-lived stars and tiny long-lived red dwarfs. Our Sun is a G-type star, roughly halfway through its roughly 10 billion year main sequence lifetime, providing stable energy output that has allowed life on Earth to evolve over billions of years. Stars similar to the Sun might provide similar conditions for life on planets orbiting at the right distances, making them prime targets in the search for potentially habitable worlds. There are perhaps tens of billions of G-type stars in our galaxy alone. The rate of star formation gives us the first piece of the framework for estimating civilizations, the foundation upon which all subsequent pieces will build through our journey tonight. Each new star represents a new opportunity for a planetary system, a new chance for the conditions that might lead to life, a new potential home for minds that might eventually wonder about the universe as we do. The stars born today will shine for millions or billions of years, lighting whatever worlds form around them, providing the energy that life requires to organize and sustain itself against entropy. This piece of the framework is among the best understood, grounded in extensive observations of star-forming regions and careful measurements of stellar populations at different ages throughout the galaxy. Astronomers can estimate the star formation rate with reasonable confidence, disagreeing only within a factor of 2 or 3, rather than the orders of magnitude uncertainty that plague later pieces of the framework. The stars are being born, have been born, will continue to be born, and this cosmic fertility provides the raw material for everything else we consider in our exploration of the question tonight. The journey from star formation to civilizations requires many more steps, each one narrowing the possibilities, each one carrying its own uncertainties about what the universe allows and what it merely permits, rarely. Stars are necessary, but not sufficient, providing the energy and the gravitational anchor for planetary systems, but guaranteeing nothing about what develops around them over cosmic time. The next step asks whether those newly formed stars actually have planets, a question that seemed almost impossible to answer just a few decades ago, but has since been illuminated by remarkable discoveries. For most of human history, the planets around other stars were entirely hypothetical, assumed to exist by some scientists, but invisible to any instrument available for observation. The idea that other stars might have planetary systems dates back centuries, but the technology to detect those planets did not exist until very recently in the long history of astronomy. The first planets around sun-like stars were discovered in the 1990s, opening a new era of astronomical research that has transformed our understanding of how common worlds might be throughout the cosmos. The search for planets around other stars began as a difficult technical challenge, requiring instruments sensitive enough to detect the tiny effects that planets produce on their host stars. Planets do not shine with their own light, but only reflect the light of their parent star, making them essentially invisible against the glare of the much brighter star they orbit. Early detection methods relied on indirect effects, subtle gravitational tugs, or slight dimmings of starlight that revealed the presence of planets without actually seeing them directly. These methods required patience, precision, and years of technological development before yielding their first confirmed discoveries. The transformation of our understanding happened remarkably quickly, once the first discoveries opened the floodgates to systematic searches using both ground-based and space-based instruments. Within 2 decades of the first confirmed detection, astronomers had catalogued thousands of planets around other stars, enough to begin drawing statistical conclusions about how common planets are throughout the galaxy. The answer that emerged from this census surprised even optimistic researchers, revealing a universe where planets are not the exception, but the rule around stars of many different types. The story of how we learned that planets are everywhere is a story of technological ingenuity and persistent observation, building machines that could detect effects too subtle for previous generations to measure. It is also a story that connects directly to the question of civilizations, because without planets, there can be no surfaces for life to develop upon, no stable environments where chemistry can become biology over billions of years. The next piece of our journey explores what those discoveries revealed about the abundance of worlds throughout the Milky Way. Worlds that might be barren or might hold possibilities we are only beginning to imagine as we look outward from our small corner of the galaxy. The stars continue forming in their dark clouds, new suns igniting to join the ancient population that already fills the galaxy with light and gravitational influence on the scales of space and time. Each new star begins surrounded by a disk of leftover material, gas and dust, that did not fall into the star itself during the collapse process, material that swirls and settles and may eventually gather into planets. The question of whether this leftover material commonly becomes planets or commonly disperses without forming worlds is the question we turn to next, a question that has been answered decisively by observations made within living memory. The galaxy is not just a collection of stars, but potentially a collection of trillions of worlds, most of them forever beyond our reach, but some of them perhaps home to life, or even minds contemplating the same vast distances that we contemplate tonight. The abundance of planets transforms the question of extraterrestrial intelligence from pure speculation into a numerical problem that can be approached with data and reason, even if significant uncertainties remain in the later pieces of the framework. Stars with planets are not rare exceptions, but common outcomes of the star formation process. And this abundance multiplies the possibilities for everything that follows. The discovery that planets orbit other stars came slowly at first, with decades of unsuccessful searches preceding the breakthroughs that would eventually reveal worlds by the thousands. For most of the 20th century, astronomers assumed planets existed around other stars, but had no way to confirm this assumption through direct observation of any kind. The planets were too small, too dim, and too close to the overwhelming glare of their parent stars to be seen with any telescope technology available at the time. Finding them would require new methods, new instruments, and new levels of precision that pushed the boundaries of what seemed technically possible. The first confirmed detection of planets around a sun-like star came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the star 51 Pegasi. This world was strange by the standards of our own solar system. A gas giant similar in mass to Jupiter, but orbiting its star in just 4 days, so close that its surface would be heated to temperatures far beyond anything in our familiar planetary neighborhood. The discovery shocked many astronomers who expected other solar systems to resemble our own, with small rocky planets close to the star and giant planets far away in the cold outer reaches. The method used to find this first planet around a sun-like star is called radial velocity detection, measuring the tiny wobble that a planet's gravity induces in its host star as both objects orbit their common center of mass. The star moves in a small circle, while the planet moves in a larger circle around the same point. And this stellar motion can be detected through careful measurement of the Doppler shift in the star's light as it moves toward and away from Earth during its wobble. The precision required is extraordinary. measuring stellar velocities of just a few meters per second, the pace of a slow walk from light years away. Following the discovery of 51 Pegasi b, more planets were found using the same technique, each one revealing new worlds with unexpected properties that expanded our understanding of what planetary systems could look like. Hot Jupiters, those gas giants orbiting very close to their stars, turned out to be relatively common and easy to detect because they produce large wobbles in short periods of time. The technique had biases toward finding large planets in close orbits, leaving smaller planets and those in wider orbits hidden for the time being until better methods and longer observational baselines became available. The real revolution in planet detection came with the launch of the Kepler Space Telescope in 2009, a mission designed specifically to answer the question of how common Earth-sized planets might be in our galaxy. Kepler used a different method called transit photometry, watching for the tiny dimming of starlight that occurs when a planet passes in front of its star, as seen from our perspective. The dimming is subtle, perhaps 1% of the star's light blocked by a Jupiter-sized planet, or less than 1/100th of 1% blocked by an Earth-sized world. Kepler stared at a single patch of sky for years, monitoring over 150,000 stars simultaneously, waiting patiently for the repeated dimmings that would reveal planets crossing in front of their stars over and over again. The mission was spectacularly successful, detecting thousands of confirmed planets and thousands more candidates awaiting confirmation through follow-up observations. The statistics that emerged from this census were remarkable, suggesting that planets are not rare, but abundant throughout the galaxy in numbers almost too large to comprehend fully. The Kepler data suggested that, on average, every star in the Milky Way has at least one planet orbiting it, and many stars have multiple planets forming complete solar systems of their own. This means our galaxy contains not just hundreds of billions of stars, but hundreds of billions of planetary systems. Trillions of individual worlds if the average system contains several planets, like our own does. The abundance exceeded what many astronomers had expected, revealing a cosmos far richer in worlds than previous generations had dared to assume without observational evidence. Among the diversity of planets discovered, some were entirely new types not represented in our solar system, worlds with no local analogue that challenged existing theories of planet formation. Super-Earths, planets larger than Earth but smaller than Neptune, turned out to be extremely common despite our solar system having no example of this type. Mini-Neptunes, worlds with thick atmospheres surrounding possibly rocky cores, appeared frequently in the data, orbiting at various distances from their host stars. The diversity of exoplanets expanded our vocabulary for describing worlds beyond our own. Rocky planets, similar in size to Earth, were found orbiting stars throughout the Kepler field of view, including some in the regions around their stars, where liquid water might exist on their surfaces, if conditions were right. These Earth-sized planets, in potentially habitable zones, became the most exciting targets for further study, worlds that might have the basic conditions necessary for life as we understand it. The Kepler mission could not tell us whether these planets actually have life, but it could tell us that such worlds exist in substantial numbers throughout the galaxy, answering one piece of the framework with actual data. The discovery of planets everywhere transformed the conversation about extraterrestrial life, from philosophical speculation into quantitative science. providing real numbers to put into the framework that scientists use to estimate the possibilities. The fraction of stars with planets, once completely unknown and freely debated, is now measured to be essentially 100%, meaning virtually every star in the galaxy has at least one world orbiting around it. This single piece of information dramatically changes the calculation of how many potential homes for life might exist throughout the Milky Way. Follow-up missions and ground-based surveys continued the census after Kepler finding planets around nearby stars that could be studied in greater detail with current and future telescopes. The TESS mission, launched in 2018, searches for planets around the brightest and closest stars to Earth, identifying worlds that are accessible for atmospheric characterization with spectroscopic instruments. These nearby planets will be the first to have their atmospheres analyzed for signs of chemistry that might indicate biological activity, if any such signs exist to be found. The diversity of stellar types hosting planets is broader than initially expected, with planets found around red dwarfs, sun-like stars, and even the remnants of dead stars in some cases. Binary star systems, where two stars orbit each other, can have planets orbiting one of the stars or both of them together in more complex configurations. The resilience of planet formation across such varied stellar environments suggests that worlds are a natural byproduct of star formation, arising almost inevitably from the disks of material that surround young stars. Planets now seem to be as common as stars themselves, transforming the Milky Way from a galaxy of lonely suns into a galaxy of countless worlds waiting to be explored, or at least catalogued from afar. The sheer number of planets changes the odds in any calculation about the possibilities for life, providing trillions of places where the conditions might be right for chemistry to become biology, if such a transition is at all probable. The abundance of worlds is now established fact, rather than hopeful assumption, grounded in data from missions that counted planets by the thousands. The question that follows naturally from this abundance is whether any of these countless worlds have the specific conditions necessary for life as we understand it. The right temperature, the right chemistry, the right environment for complexity to emerge and persist. Having a planet is not enough if that planet is a frozen ball of ice in the outer darkness, or a molten world too close to its star for any chemistry to proceed without immediate destruction. The framework asks next about habitable worlds, those that might provide the conditions where life could at least have a chance to begin and develop over geological time. The search for habitable worlds focuses on the concept of the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface under the right atmospheric conditions. This zone is sometimes called the Goldilocks zone, a region that is not too hot and not too cold, but just right for water to flow as a liquid rather than freeze as ice or boil away as vapor. The boundaries of this zone depend on the star's brightness and temperature, with hotter stars having habitable zones farther out, and cooler stars having habitable zones tucked closer to the stellar surface. Finding planets in habitable zones has become a major focus of exoplanet research, with specific attention paid to Earth-sized worlds in these favored regions around stars similar to our Sun. The Kepler mission and its successors have identified numerous candidates. Planets that are roughly Earth-sized and orbiting at roughly the right distance from their stars to potentially have liquid water if their atmospheres cooperate. Whether any of these candidates actually have water, or atmospheres, or surfaces remotely similar to Earth, remains unknown without more detailed observations that future telescopes may provide. The discovery that planets are everywhere is perhaps the most significant change in our understanding of the cosmos since humans first began looking up at the stars and wondering what might be out there. In just a few decades, we have gone from knowing of only 8 planets in a single solar system to knowing of thousands of planets in hundreds of different systems across our galactic neighborhood. The implications for the question of life and intelligence are profound, multiplying the places where we might look and the odds that something interesting might be found if we look carefully enough in the right places. The habitable zone around a star defines a ring of space where temperatures might allow liquid water to exist on a planet's surface, creating conditions that could support life as we understand it from our experience on Earth. This zone is not a sharp boundary, but a gradual transition, with the inner edge marking where a planet would likely become too hot to retain surface water, and the outer edge marking where water would likely freeze into permanent ice. The location and width of the zone depend on the star, with brighter stars having zones farther from the stellar surface, and dimmer stars having zones tucked in close. For our Sun, the habitable zone extends roughly from the orbit of Venus to somewhat beyond the orbit of Mars, a range of distances where temperatures could support liquid water under the right atmospheric conditions. Earth sits comfortably within this zone, receiving enough solar energy to warm its surface above freezing, while not receiving so much that its oceans boil away into space. Venus, just inside the inner edge, experienced a runaway greenhouse effect that left it with surface temperatures hot enough to melt lead, despite receiving only slightly more solar radiation than Earth does. Mars sits at, or just beyond, the outer edge of the Sun's habitable zone, and its thin atmosphere cannot trap enough heat to maintain liquid water on its surface today, though evidence suggests water flowed there billions of years ago, when conditions were different. The examples of Venus and Mars in our own solar system illustrate that being in or near the habitable zone is not sufficient for a world to actually be habitable, since atmospheric composition and other factors play crucial roles in determining surface conditions. A planet can be in the right place but have the wrong atmosphere, or be in a marginal position but compensate through atmospheric effects. The habitable zone concept provides a useful starting point for identifying potentially life-bearing worlds around other stars, giving astronomers specific regions to focus their attention when searching for Earth-like conditions. Kepler and other missions have identified numerous planets orbiting within the habitable zones of their host stars, suggesting that worlds at the right temperature for liquid water are not rare in our galaxy. Whether those worlds actually have water, have atmospheres, have surfaces where liquid water could exist, requires additional observations beyond what simple transit detection can provide. Red dwarf stars, the most common type of star in the galaxy, have habitable zones located very close to the stellar surface, because these small, cool stars produce relatively little light and heat. A planet in the habitable zone of a red dwarf might orbit its star in just a few days or weeks, completing many orbits for every single orbit Earth makes around the Sun. This close proximity brings potential challenges for habitability, including intense stellar flares that could strip away atmospheres, and tidal locking that might leave one hemisphere in permanent day and the other in permanent night. The question of whether planets around red dwarfs can truly be habitable remains actively debated among scientists studying these systems in detail. Some researchers argue that thick atmospheres could protect planetary surfaces from stellar flares and distribute heat from the day side to the night side, maintaining conditions suitable for life, even in these unusual configurations. Others worry that the intense early activity of young red dwarfs might sterilize or strip the atmospheres from close-in planets before life has a chance to establish itself. The answer matters enormously for estimates of habitable worlds, since red dwarfs vastly outnumber Sun-like stars. Beyond the traditional habitable zone defined by liquid water on surfaces, some scientists argue that habitable environments might exist in other configurations that expand the possibilities for life in the galaxy. Moons of giant planets located outside the traditional habitable zone might have liquid water beneath icy surfaces, heated by tidal forces rather than stellar radiation, potentially harboring life in subsurface oceans. In our own solar system, Jupiter's moon Europa and Saturn's moon Enceladus are considered possible abodes for life precisely because of subsurface oceans maintained by tidal heating from their giant planet hosts. The number of potentially habitable worlds in the galaxy depends on how broadly we define habitability. Whether we restrict attention to surface water in traditional habitable zones or expand consideration to include subsurface environments heated by other means. Conservative estimates focusing only on Earth-like planets in traditional habitable zones around Sun-like stars still yield billions of potential targets within the Milky Way alone. More expansive definitions that include worlds around red dwarfs and moons of giant planets multiply this number significantly, potentially yielding tens of billions of potentially habitable environments waiting to be discovered or studied. Kepler's statistical analysis suggests that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone, a remarkable frequency that implies billions of such worlds scattered throughout the galaxy. These estimates carry uncertainties, depending on exactly how Earth-sized and habitable zone are defined. But even the most conservative interpretations suggest that suitable worlds are far from rare. The piece of the framework dealing with potentially habitable planets per star is now constrained by actual observations rather than speculation, though significant uncertainties remain about what these worlds are actually like. Finding a planet in the habitable zone tells us about temperature, but says nothing directly about whether that world has an atmosphere, whether that atmosphere contains water vapor, whether the surface has oceans or continents, or conditions anything like Earth. The transit method that found most of these planets measures size and orbital period, but cannot directly measure mass, composition, or atmospheric properties without additional observations using other techniques. The next generation of telescopes aims to characterize the atmospheres of some of these worlds, looking for signs of water, oxygen, methane, or other gases that might indicate interesting chemistry or even biological activity. The diversity of planets discovered makes clear that Earth-sized does not mean Earth-like, as worlds of similar size could have vastly different compositions, atmospheres, and surface conditions. Some Earth-sized planets might be water worlds covered entirely by global oceans, with no land to break the surface. Others might be dry, rocky deserts with little or no water at all. Habitable zone or not, the term Earth-sized, referring only to physical dimensions and not to anything about chemistry or environment. The search for truly Earth-like worlds continues, with increasingly capable instruments designed to tease out the subtle signals that might reveal whether distant planets have atmospheres similar to our own. The James Webb Space Telescope has already begun studying the atmospheres of some exoplanets, detecting the presence of various molecules in the air of worlds orbiting other stars. These early atmospheric studies focus mainly on larger planets or planets orbiting very close to small stars, where the signals are strongest. But technology is steadily advancing towards smaller, more Earth-like targets. The framework's piece about habitable worlds is now partially filled in with real data, showing that such worlds exist in substantial numbers throughout the galaxy, even under relatively conservative definitions of what constitutes potentially habitable. Whether these worlds are actually suitable for life depends on factors we cannot yet measure for most of them, including atmospheric composition, surface conditions, magnetic field strength, and many other details that determine whether a planet in the right zone is truly a place where life might arise. The next piece of the framework asks an even harder question, one that takes us from astronomy into biology, from observing distant worlds to wondering about the origin of life. The transition from potentially habitable world to actually inhabited world requires something extraordinary to happen: the emergence of life from non-living chemistry, a process we call abiogenesis, that happened at least once on Earth, but whose likelihood on any given suitable world remains one of the deepest mysteries in science. Having the right conditions is not the same as having life arise in those conditions. And we have no way to know from astronomical observation alone whether life is common or rare on worlds that could theoretically support it. The question of how life begins touches on chemistry, geology, planetary science, and biology all at once, requiring an understanding of how complex self-replicating molecules could arise from simpler precursors in the environments of early planets. This is where the framework moves from questions we can partially answer with telescopes to questions that require understanding processes we have never observed and may never be able to observe directly. The origin of life on Earth is lost in the deep past, leaving only clues in the chemistry of living cells and the geological record of early conditions that might hint at how it all began. Life exists on Earth, and that simple fact tells us that the transition from chemistry to biology is possible under at least some conditions that existed on at least one world in the history of the universe. What we cannot determine from this single example is how likely that transition is, whether it happens on most suitable worlds or only on a tiny fraction through chance events so improbable that Earth might be the only place it ever occurred. The framework asks about this probability, the fraction of suitable worlds where life actually emerges. And we must admit honestly that we do not know the answer despite centuries of scientific investigation. The earliest evidence for life on Earth dates to approximately 3.5 billion years ago, perhaps earlier, in rocks that preserve chemical signatures or microscopic structures that appear biological in origin. The Earth itself formed about 4.5 billion years ago, meaning that life appeared within the first billion years of our planet's existence, possibly within the first few 100 million years, once conditions stabilized enough for chemistry to proceed. This relatively rapid emergence might suggest that life arises easily wherever conditions permit, or it might simply mean we got lucky early and have been building on that lucky start ever since. The conditions on early Earth were very different from today, with an atmosphere lacking oxygen, intense bombardment from leftover debris in the solar system, and volcanic activity reshaping the surface continuously. Oceans formed relatively early, providing the liquid water that appears essential for life as we know it, though the exact timing and extent of early oceans remains a subject of ongoing research. Somewhere in those ancient waters, or perhaps in hot springs on land, or in deep-sea hydrothermal vents, the first self-replicating molecules began the chain of chemistry that would eventually produce all the diversity of life we see today. The problem of understanding how life begins, called the origin of life problem, or abiogenesis, has occupied scientists for over a century without yielding a definitive answer that everyone accepts as correct. We know that life is based on complex molecules like DNA, RNA, and proteins that carry information and catalyze chemical reactions, but how these molecules first arose from simpler precursors remains unclear. Several competing hypotheses propose different pathways and different environments for the origin of life, each with supporting evidence and each with unresolved challenges that prevent consensus. One influential hypothesis suggests that life began in an RNA world, where RNA molecules served both as carriers of genetic information and as catalysts for chemical reactions before DNA and proteins took over these roles separately. RNA can do both jobs, unlike DNA, which stores information well, but does not catalyze reactions, or proteins, which catalyze reactions well, but do not replicate themselves. The RNA world hypothesis suggests that simpler, self-replicating RNA molecules gradually evolved into the more complex cellular life we see today, with DNA taking over information storage and proteins taking over catalysis as evolution proceeded. Another hypothesis locates the origin of life in deep-sea hydrothermal vents, where hot, mineral-rich water emerges from the Earth's crust and mixes with cold ocean water, creating gradients of temperature and chemistry that might drive the reactions necessary for life to begin. These vents provide energy independent of sunlight, could have sheltered early life from the intense bombardment affecting the surface, and contain minerals that can catalyze reactions important for metabolism. Some of the oldest life forms on Earth today thrive in vent environments, potentially representing a connection to these ancient beginnings. Laboratory experiments have shown that the basic building blocks of life can form spontaneously under conditions thought to exist on early Earth, providing some support for the idea that life's chemistry is not implausible given the right environment. The famous Miller-Urey experiment in 1953 showed that amino acids, the building blocks of proteins, could form from simple gases like methane, ammonia, and hydrogen when energy was added through electrical sparks, simulating lightning. Subsequent experiments have produced nucleotides, sugars, and other molecules important for life under various early Earth scenarios. Yet there remains an enormous gap between producing simple building blocks and producing self-replicating systems that could be called alive by any reasonable definition of the term. The simplest living cells today contain thousands of different molecules, working together in intricate networks of chemical reactions that seem impossibly complex to have arisen all at once from non-living. Chemistry. The gap between chemistry and biology is wider than early researchers appreciated, and bridging it in the laboratory has proven extraordinarily difficult, despite decades of trying. If life's origin was essentially inevitable given the right conditions and enough time, then life should be common throughout the universe, wherever suitable planets exist in sufficient numbers. This optimistic view suggests that the universe might be teeming with life, most of it microbial and simple, but life nonetheless, carrying out the basic processes of metabolism and reproduction on countless worlds, orbiting countless stars. The rapid emergence of life on Earth supports this view, suggesting that once conditions became suitable, life appeared quickly, as if the transition from chemistry to biology requires only opportunity. If life's origin was a spectacularly unlikely accident, a chance combination of circumstances that might happen only once in a galaxy or once in a universe, then we might be effectively alone, despite the abundance of potentially habitable worlds. This pessimistic view suggests that suitable planets are empty, sterile rocks where chemistry never makes the leap to biology, no matter how long you wait. The fact that life originated on Earth tells us nothing about the probability, if the probability is extremely low, and we are simply the winners of a cosmic lottery who exist only because we are here to ask the question. We have no way to distinguish between these possibilities with current evidence, which is why this piece of the framework carries such enormous uncertainty in any attempt to estimate the number of civilizations in the galaxy. The fraction of suitable worlds where life arises might be nearly 100%, or it might be effectively 0. And we cannot tell from our single example which end of this range is closer to reality. Future discoveries of life elsewhere in our solar system, or through spectroscopic detection of biological signatures in exoplanet atmospheres, would help resolve this uncertainty. But no such discoveries have occurred yet. The search for life in our own solar system continues, with missions designed to explore Mars, Europa, Enceladus, and other worlds where conditions might support at least microbial life beneath the surface. Mars once had liquid water on its surface, and recent missions have searched for signs of past or present life in the Martian rocks and soil, without definitive results so far. Europa's subsurface ocean, kept liquid by tidal heating from Jupiter, represents another possible abode for life that future missions will investigate with landers, and perhaps eventually robotic submarines. Finding life on Mars or Europa would be transformative for our understanding of life's likelihood, proving that the transition from chemistry to biology can happen more than once in a single solar system. If life arose independently on two different worlds, in our own neighborhood, that would strongly suggest life is common throughout the universe, wherever suitable conditions exist. If our solar system proves to have only one origin of life on Earth, and nowhere else, that would say less about the probability, since absence of evidence is not evidence of absence in environments we have barely explored. The possibility that Martian life and Earth life share a common origin complicates this picture, since rocks blasted from one planet by asteroid impacts can eventually land on the other planet after traveling through space for thousands or millions of years. If life originated on Mars and seeded Earth through such a rock exchange, or vice versa, then finding life on Mars would not constitute an independent origin and would tell us less about life's probability elsewhere. Scientists would need to examine any Martian life carefully to determine whether it represents an independent emergence or a relative of Earth life transported between planets. The framework acknowledges this uncertainty honestly, representing it as a factor that might be close to 1 or might be vanishingly small, depending on which scientific intuitions prove correct when more evidence becomes available. Optimists argue that the chemistry of life is written into the physics of the universe, arising wherever conditions permit, as a natural outcome of atoms combining into molecules, combining into polymers, combining into self-replicating systems over billions of years. Pessimists argue that the specific pathway from chemistry to biology may be so narrow, requiring so many coincidences, that Earth represents an almost miraculous exception in a mostly lifeless cosmos. The question of life's origin leads naturally to the next question in the framework: whether life, once established, tends to develop intelligence and technology, or tends to remain simple and microbial for billions of years, without ever producing minds capable of wondering about the universe. On Earth, life existed for billions of years as single-celled organisms before anything we would recognize as complex appeared. And complex life existed for hundreds of millions of years before anything we would recognize as intelligent evolved. The path from first life to first mind is long and uncertain, and we must ask whether Earth's path represents a common journey or a rare exception. Life on Earth remained single-celled for roughly 3 billion years, with bacteria and archaea as the only inhabitants of the planet for most of its biological history. These simple organisms were extraordinarily successful, colonizing every environment from boiling hot springs to frozen Antarctic ice, from the deepest ocean trenches to high in the atmosphere, thriving in conditions that would destroy more complex life. For billions of years, this was all life was: microscopic cells dividing and evolving, without any apparent tendency to become more complex or more intelligent over time. The emergence of complex multicellular life happened relatively recently in Earth's history. Only about 600 million years ago, in an event sometimes called the Cambrian explosion, when the fossil record suddenly reveals a diversity of animal body plans that had not existed before. Something changed, perhaps rising oxygen levels, perhaps evolutionary innovations in how cells could cooperate and specialize. That allowed life to build larger and more complex structures than the simple colonies of identical cells that preceded them. Once this transition occurred, evolution produced an astonishing variety of complex organisms over the following hundreds of millions of years. Even after complex multicellular life appeared, intelligence was not an inevitable or obvious direction for evolution to take, with most lineages exploring other strategies for survival and reproduction. Plants have thrived for hundreds of millions of years without anything resembling nervous systems, succeeding through chemistry and growth rather than thought and behavior. Many animal lineages developed simple nervous systems adequate for their ecological roles, without any trend toward greater intelligence over time. Intelligence is expensive, requiring large brains that consume significant energy, and evolution does not always favor the more intelligent option. The dinosaurs dominated Earth for 165 million years, far longer than mammals have been prominent, without any lineage, developing technology, or what we would recognize as human-level intelligence. Their success as a group suggests that intelligence is not the only path to evolutionary success, perhaps not even a particularly good path compared to alternatives like speed, strength, armor, or venom. If the asteroid had not struck 66 million years ago, dinosaurs might still dominate the Earth, and mammals, including the lineage leading to humans, might never have had the opportunity to diversify and fill the ecological niches left empty by the extinction. The extinction of the dinosaurs opened ecological opportunities that mammals quickly exploited, diversifying into the niches left empty by the vanished reptiles over the following millions of years. Primates emerged as one branch of this mammalian radiation, tree-dwelling creatures with grasping hands and forward-facing eyes suited for life in forest canopies. Over tens of millions of years, some primate lineages developed larger brains relative to body size, more complex social structures, and eventually the capacity for abstract thought and language that distinguishes humans from other animals. Human-level intelligence appeared only in the last few 100,000 years, a geological eye blink after billions of years of life and hundreds of millions of years of complex life on Earth. Our species, Homo sapiens, represents one twig on one branch of one lineage of mammals. And our particular form of intelligence is not shared by any other species currently alive, despite many species having notable cognitive abilities. The question is whether we represent a common outcome of evolution that would repeat on other worlds, or a fluke that depended on specific contingencies of Earth's history. Several lines of evidence suggest that evolution does tend to produce increasing intelligence over time, at least in some lineages, under some circumstances, supporting cautious optimism about intelligence arising on other worlds. Independent evolution of intelligence has occurred in multiple lineages on Earth, with octopuses, crows, dolphins, and great apes all developing notable cognitive abilities through separate evolutionary paths. This convergent evolution toward intelligence suggests that minds may be a common solution to certain ecological challenges, emerging repeatedly when conditions favor cognition over other strategies. Yet none of these other intelligent lineages has developed technology anything like human technology, suggesting that the specific kind of intelligence that builds telescopes and sends radio signals may be exceptionally rare even among generally intelligent species. Dolphins are intelligent, but live in an environment where fire is impossible, and manipulation of objects is limited by their body plan and environment. Octopuses are intelligent but short-lived and solitary, without the social structures that seem to support cultural transmission of knowledge across generations. Intelligence alone is not enough. The framework asks about intelligence in a specific sense, the kind of intelligence that can lead eventually to technology capable of interstellar communication. Not just general cognitive ability that might make an organism successful in its environment. This framing biases the question toward human-like intelligence, since we are the only example we have of technology producing intelligence, while acknowledging that other forms of intelligence might exist that we would fail to recognize or that would not produce detectable signals. An intelligent but non-technological species would be invisible to our current search methods, even if common throughout the galaxy. The fraction of life-bearing planets that develop intelligence is one of the most uncertain pieces of the framework, with estimates ranging from nearly 100% to far less than 1%, depending on assumptions about whether Earth's path is typical or exceptional. Optimists point to the convergent evolution of intelligence and the general trend toward larger brains in several lineages over Earth's history as evidence that intelligence may be favored by evolution under many circumstances. Pessimists point to the billions of years life spent as single cells and the many mass extinctions that reset the playing field as evidence that complex intelligence depends on contingencies that might rarely align. The question connects to deep issues in evolutionary biology about whether evolution has direction or tendency, whether certain outcomes are more probable than others, or whether history is dominated by accident and contingency with no predictable outcomes. Stephen Jay Gould famously argued that if we could replay the tape of life from the beginning, the outcome would be completely different, with no guarantee that humans or anything like us would ever appear. Other scientists argue that certain forms and solutions are so advantageous that evolution would find them repeatedly, channeling life towards similar endpoints through different paths. The length of time required for intelligence to evolve on Earth, roughly 4 billion years from life's origin to human civilization, suggests that intelligence may require a long period of stable conditions to emerge, potentially limiting the opportunities even on otherwise suitable worlds. A planet must remain habitable for billions of years, while life evolves from simple origins to complex intelligence, requiring a stable star, stable orbit, and absence of catastrophic events that reset the evolutionary clock. Not all potentially habitable planets may remain habitable long enough for intelligence to emerge. The emergence of human intelligence depended on a specific sequence of events, from the symbiotic origin of complex cells to the development of multicellularity, to the colonization of land, to the extinction of dinosaurs, to the evolution of primates in African forests, to the development of bipedalism and tool use on the African savanna. Change any of these events, and the history of life might have proceeded differently, perhaps never producing anything like human intelligence, even on a planet that was biologically successful by other measures. The contingency of our own existence makes estimating the probability of intelligence elsewhere profoundly difficult. Despite these uncertainties, the framework includes this factor and requires some estimate, whether optimistic or pessimistic, to proceed with the calculation of how many civilizations might exist. Scientists making such estimates typically acknowledge the uncertainty and explore how different assumptions about intelligence change the final result, producing a range of possibilities rather than a single confident answer. The honest approach recognizes that we are guessing, informed by our one example, unable to know for certain whether that example is typical or extraordinary. The evolution of intelligence, if it occurs, leads to the next question in the framework: whether intelligent species develop the technology necessary to communicate across interstellar distances, making their presence detectable to others who might be searching. Intelligence without technology would be invisible to our current search methods, no matter how profound or complex the thoughts of beings living on distant worlds might be. The framework is specifically interested in technological intelligence, the kind that builds things and broadcasts signals, because that is the kind we might have any hope of detecting from our vantage point among the stars. Technology represents a new kind of power in the universe, the ability to reshape matter and energy for purposes that evolution never anticipated, extending the reach of intelligence far beyond biological limits. On Earth, technology developed gradually over millions of years, from the first stone tools used by early human ancestors to the satellites and radio telescopes that extend our senses across the cosmos today. The transition from intelligent species to technologically capable species was not instantaneous, but required countless innovations, building upon each other over vast spans of time. The earliest evidence of tool use by human ancestors dates back several million years, with simple stone tools appearing in the archaeological record from species that were clearly intelligent, but not yet human in the modern sense. These early tools were simple, rocks shaped to have sharp edges for cutting or scraping, but they represented a new kind of interaction with the world, using objects to extend the capabilities of the body. Tool use itself is not unique to humans, with crows, chimps, and other species demonstrating the ability to use objects to achieve goals. But humans uniquely developed the capacity to improve tools systematically across generations. Fire was a transformative technology, providing warmth, protection, cooking, and eventually metallurgy, each application opening new possibilities that previous generations could not have imagined. Control of fire appeared perhaps 1 million years ago, though dating the earliest controlled use is difficult with available evidence. Cooking allowed extraction of more energy from food, potentially supporting the metabolic demands of larger brains, in a feedback loop where technology enabled further biological development. The domestication of fire may have been a crucial step toward the technological civilization we have become. Agriculture appeared only about 10,000 years ago, a recent development after hundreds of thousands of years of human existence as hunter-gatherers following resources across landscapes without permanent settlements. The ability to grow food in one place allowed permanent villages, then cities, then the accumulation of knowledge and resources that enabled further technological development in a cascading progression. Writing appeared about 5,000 years ago, allowing information to be stored and transmitted across generations without relying solely on memory and oral tradition. Another crucial step toward the civilization that would eventually build telescopes. The pace of technological change accelerated dramatically in recent centuries, with discoveries and inventions building on each other faster than ever before in human history. The scientific revolution of the 16th and 17th centuries established methods for systematically understanding nature, leading to insights that enabled engineering and technology impossible for previous generations. The Industrial Revolution of the 18th and 19th centuries harnessed fossil fuels to power machines, multiplying human physical capabilities as tools had once multiplied our ability to cut and shape materials. Electricity transformed civilization again, enabling communication at the speed of light through telegraph and later radio, television, and the internet that now connects billions of people across the planet. The development of radio in the late 19th century created the first technology capable of sending signals beyond Earth. Unintentionally at first, as radio broadcasts leaked into space. Later, intentionally, as scientists conceived of using radio for interstellar communication. Radio signals travel at the speed of light, and our earliest broadcasts have now traveled more than 100 light-years from Earth, spreading outward as an expanding sphere of evidence that a technological species exists here. The framework asks about this specific transition from intelligent species to species capable of interstellar communication, because that capability is what makes detection possible across the vast distances separating stars in the galaxy. Many paths could lead to intelligence without leading to radio transmitters or other technologies that might produce detectable signals, leaving intelligent species invisible to searches that depend on technological signatures. An intelligent species that developed underwater might never discover fire or electricity, pursuing different technological paths that might be equally sophisticated but invisible to radio searchers. Human technology developed on land, in an environment where fire was possible, where manipulation of objects came naturally to creatures with hands, where resources could be accumulated and knowledge recorded in permanent forms. Had our ancestors remained in the oceans, or had our planet been covered entirely in water, the path to radio telescopes might never have opened, regardless of how intelligent the minds that evolved there. The fraction of intelligent species that develop technology capable of interstellar communication remains deeply uncertain, with estimates ranging from nearly all to a small minority depending on assumptions about evolutionary pressures and environmental constraints. Some scientists argue that once a species achieves human-level intelligence, the development of technology follows almost inevitably, given enough time and the right environmental conditions. Others point out that human-style technology requires specific circumstances that might be rare, including fire, metallurgy, and the ability to manipulate the environment in ways that underwater or underground civilizations could never achieve. Even among land-dwelling species with hands and fire, the path to radio technology was not straightforward or inevitable, requiring specific discoveries in specific sequences that might have happened differently or not at all. The discovery of electromagnetism, the understanding of radio waves, the engineering of transmitters and receivers, all required insights that emerged from particular historical circumstances, in particular cultures, at particular times. Had history unfolded differently, we might have developed other technologies while never discovering the principles that make radio communication possible across interstellar distances. The question of what fraction of intelligent species reach this technological threshold matters enormously for estimating how many civilizations we might detect with our current search methods and instruments. If nearly all intelligent species eventually develop radio technology, then the number of potentially detectable civilizations could be large, limited mainly by other factors in the framework. If the fraction is small, perhaps only 1 in 10 or 1 in 100, then even a galaxy filled with intelligent life might contain relatively few civilizations broadcasting signals we could hope to receive. Beyond developing the technology, there is the question of whether civilizations choose to use it for interstellar communication, actively or passively revealing their presence to anyone listening across the light years. Our own radio leakage has been spreading into space since the early 20th century. That these signals were not intended for interstellar communication and are relatively weak compared to what a deliberate beacon might produce. A civilization that wanted to remain hidden could presumably do so by limiting emissions, though the motivations for such hiding are speculative and depend on assumptions about how civilizations think about their place in the cosmos. Some civilizations might broadcast deliberately, either calling out in hopes of contact or sending information as a gift to any listener regardless of whether a response was possible. The Arecibo message, sent in 1974 toward a distant star cluster, was a deliberate, if mostly symbolic attempt at interstellar communication from Earth. Future civilizations might construct powerful beacons visible across the galaxy, or they might remain silent for reasons we cannot currently imagine or predict from our single example. The technologies we search for reflect our own capabilities and assumptions, primarily radio waves, because that is what we can detect with current instruments and what we know how to produce. Other civilizations might communicate using lasers, gravitational waves, or methods we have not yet discovered or cannot yet detect with our current understanding of physics. The search for extraterrestrial intelligence necessarily begins with what we know, but it must remain open to the possibility that advanced civilizations use methods beyond our current detection capabilities. Radio waves travel at the speed of light, meaning any signal we detect left its source years, decades, centuries, or millennia before reaching Earth, depending on the distance to its origin. A signal from a star 1,000 light-years away would have left before the Norman conquest of England, carrying information about conditions that prevailed when the message began its journey. Communication at interstellar distances is inherently a conversation across time as well as space, with round-trip communication times measured in lifetimes or civilizations. The galaxy contains perhaps 200 billion stars spread across a disk, 100,000 light-years in diameter, meaning even nearby stars are separated by distances requiring years for light to cross between them. Our nearest stellar neighbor, the Alpha Centauri system, is about 4 light-years away, close by galactic standards, but still requiring 8 years for a round-trip message exchange at the speed of light. More distant stars require proportionally longer, making rapid conversation impossible and any communication necessarily patient and long-term in its expectations. This reality shapes what interstellar communication might look like, if it exists, favoring transmissions that carry meaning without requiring immediate response. Perhaps mathematical concepts or cultural information that rewards any receiver regardless of the possibility of dialogue. The framework does not specify what form communication might take, only that some civilizations might produce detectable signals that could reveal their existence to patient observers searching across the electromagnetic spectrum. The fraction of intelligent civilizations that become detectable through technology represents a filter in the chain of probabilities, another step where the enormous number of possibilities narrows toward whatever final answer the universe actually provides. Combined with all the previous steps, from star formation through planetary systems, through habitable worlds, through the emergence of life and intelligence, this factor helps determine whether the galaxy hosts many technological civilizations or few. Our own civilization has been capable of interstellar radio communication for roughly 1 century, a brief moment in the 4.5 billion-year history of our planet, and the approximately 300,000-year history of our species. Whether we will continue broadcasting for another century or another million years depends on choices and circumstances yet to unfold. Connecting this factor to the next and most uncertain piece of the framework, the question of how long technological civilizations persist. The longevity of technological civilizations represents perhaps the most uncertain and consequential piece of the entire framework. The factor that could determine whether the galaxy teems with detectable life or remains largely silent across the vast distances between stars. How long a civilization remains capable of interstellar communication matters enormously, because even if many civilizations arise throughout the galaxy's history, they must overlap in time to have any chance of detecting one another across the light years separating them. Consider a simple illustration of why longevity matters so profoundly for the question of whether we might detect other civilizations or be detected by them. The Milky Way galaxy is approximately 13 billion years old, while human technological civilization has existed for roughly 1 century, a ratio of about 130 million to 1. If a typical civilization lasts only 100 years, and civilizations arise randomly throughout galactic history, the chance of two existing at the same time becomes vanishingly small, despite potentially large numbers arising over billions of years. Longer-lived civilizations dramatically increase the odds of temporal overlap, making detection more plausible, even if fewer civilizations arise in total across the galaxy's entire history. A civilization lasting 1 million years has 10,000 times more opportunity to overlap with another than one lasting only 100 years, simply by persisting through more of galactic time. If civilizations typically endure for billions of years, approaching the age of the galaxy itself, then even modest numbers arising throughout cosmic history would likely coexist today. The framework requires estimating how long a technological civilization typically remains detectable. But we have only one example to examine: our own civilization, which has been technological for about 1 century and whose future longevity remains entirely unknown. We cannot know whether humanity will exist as a technological civilization 1,000 years from now, 1 million years from now, or whether some catastrophe or transformation will end our detectable phase within the next century. The possibilities span an enormous range, from civilizations that destroy themselves shortly after achieving technology, to civilizations that persist for billions of years, spreading across their home galaxies and beyond. Pessimistic scenarios imagine civilizations typically lasting only decades or centuries before succumbing to nuclear war, environmental collapse, pandemic disease, or other existential catastrophes enabled or accelerated by the same technologies that make them detectable. Optimistic scenarios envision civilizations learning to manage existential risks and continuing indefinitely, perhaps spreading to multiple star systems to ensure survival against any single-point catastrophe. Human history offers ambiguous evidence for both possibilities, with civilizations rising and falling throughout recorded time, some persisting for centuries or millennia before transformation or collapse. The Roman Empire lasted roughly 500 years in the West, and over 1,000 years in the East. The ancient Egyptian civilization persisted for 3,000 years. And Chinese civilization has continued in various forms for even longer. These examples suggest civilizations can achieve considerable longevity, though none had the technological power to either destroy themselves utterly or spread beyond their home planet. The 20th century introduced genuinely new considerations with the development of nuclear weapons, which for the first time gave humanity the power to devastate civilization globally within hours. The Cold War brought humanity closer to self-destruction than any previous era. With the Cuban Missile Crisis of 1962 representing perhaps the closest approach to nuclear war between superpowers. That we survived this period might be evidence of resilience, or might simply be luck that could run out in future confrontations. Climate change represents another long-term challenge to civilizational persistence, with human activity altering the planet's climate systems in ways that could destabilize agriculture, flood coastal cities, and trigger cascading effects across interconnected natural and human systems. The challenge differs from nuclear war in developing slowly over decades rather than striking suddenly, but could prove equally destabilizing if not managed effectively through global cooperation and technological innovation. Pandemic disease has repeatedly devastated human populations throughout history, and advances in biotechnology raise the possibility of engineered pathogens more dangerous than any natural disease, a risk that grows as biotechnology becomes more accessible and more powerful. The coronavirus pandemic of 2020 demonstrated how quickly disease can spread through modern transportation networks and how challenging coordinated global response remains even for a relatively manageable pathogen. Artificial intelligence represents a newer consideration, with rapidly advancing capabilities raising questions about whether humanity can maintain meaningful control over systems that might eventually exceed human intelligence in various domains. The long-term trajectory of artificial intelligence remains deeply uncertain, with possibilities ranging from beneficial tool to existential threat, depending on how the technology develops and how society manages its deployment. These risks are specific to humanity and our particular historical moment, but analogous challenges might face any technological civilization, regardless of its biology or history. The discovery of nuclear physics, the alteration of climate through industrial activity, the development of advanced biotechnology, and the creation of artificial intelligence might be typical transitions that all technological civilizations face, with outcomes determining whether they persist or perish. The concept of a great filter has emerged to describe this possibility. The idea that some step in the progression from non-living matter to galaxy-spanning civilization is extremely difficult to pass, filtering out almost all attempts along the way. If the filter lies behind us, in the origin of life or the evolution of intelligence, then our existence suggests these steps are extraordinarily rare, but that civilizations surviving to our stage might persist indefinitely. If the great filter lies ahead of us, in some challenge that technological civilizations typically fail to survive, then even a galaxy that has produced many technological civilizations throughout its history might be nearly empty now, populated only by the wreckage of failed experiments and perhaps a few rare survivors. The silence of the cosmos, the absence of obvious evidence for extraterrestrial intelligence despite billions of years of opportunity, might be evidence that the filter is powerful and that few civilizations pass through it successfully. A more hopeful possibility is that civilizations typically survive their dangerous adolescence, learning to manage existential risks and transitioning to stable states that persist for astronomical timescales. A civilization that survives its first few centuries of nuclear weapons, climate change, and biotechnology might develop the wisdom and institutions to persist indefinitely, having demonstrated the ability to manage global-scale challenges cooperatively. Some scientists suggest that long-lived civilizations might transform in ways that make them less detectable, rather than ceasing to exist entirely, perhaps transitioning to modes of existence that no longer involve broadcasting electromagnetic signals into space. A civilization that moves underground or into virtual reality, or towards some post-biological form might effectively disappear from our searches, even while continuing to exist in ways we cannot easily imagine or detect. Others suggest that civilizations might actively choose to remain silent, recognizing that broadcasting presence might attract unwanted attention from other civilizations with unknown intentions. The dark forest hypothesis proposes that civilizations remain quiet because the risks of contact outweigh the benefits, leaving the galaxy apparently empty, even if filled with cautious, hidden minds. The true value of this factor in the framework remains unknown and might be unknowable from our current position in history. With our single example and limited perspective on the possibilities that the universe offers, we can only observe that we are here, that we have been technological for about a century, and that our future remains unwritten, dependent on choices yet to be made and circumstances yet to unfold. What we choose to do with our own civilization in the coming decades and centuries will contribute one data point to the cosmic average. Our longevity, joining whatever other civilizations have achieved throughout galactic history. Whether we last 1 century or 1 billion years will be determined by how well we manage the risks we have created and the opportunities that technology provides for expansion beyond our vulnerable single planet. The framework connects longevity to all the previous factors through simple multiplication, combining uncertainties about star formation and planetary systems and life and intelligence and technology with this final, most uncertain factor to produce estimates of how many civilizations might exist at any given moment. The range of possible answers spans many orders of magnitude, from a galaxy teeming with millions of technological civilizations to one where we might be utterly alone. The framework now stands complete before us, a chain of connected questions that together approach the profound mystery of whether other minds exist among the stars we see scattered across the night sky. Each piece builds upon those that came before, starting from the vast number of stars in our galaxy and progressively narrowing through planets, habitable worlds, life, intelligence, technology, and finally, longevity, to reach some estimate of how many civilizations might currently share this cosmic moment with us. The multiplication of these factors proceeds like filtering water through ever finer screens, each screen removing some portion of what passed through the previous one, until whatever remains represents the final answer. Starting with hundreds of billions of stars in the Milky Way, each subsequent factor reduces that number. Some factors now reasonably well known from observations, others remaining deeply uncertain and speculative, dependent more on assumptions than evidence. The first piece, the rate at which stars form, is now well measured at roughly 1 to 3 new stars per year in our galaxy, with modern observations constraining this value far better than scientists could estimate decades ago. This factor provides the raw material from which everything else must emerge, the stellar nurseries where new suns ignite and new planetary systems might eventually form around them. The second piece, the fraction of stars with planets, has been revolutionized by the discovery of thousands of worlds orbiting other stars, revealing that planetary systems are common rather than rare. Current estimates suggest nearly every star hosts at least one planet, perhaps more, with the galaxy containing more planets than stars, according to the best available observations. This factor, once highly uncertain, now stands on solid observational ground. The third piece, the number of potentially habitable worlds per planetary system, remains less certain, but increasingly constrained by observations of Earth-sized planets in habitable zones around their stars. Perhaps 20 to 40% of Sun-like stars host rocky planets in zones where liquid water could exist on their surfaces, suggesting habitable real estate is not vanishingly rare across the galaxy. These astronomical factors, the ones involving stars and planets, are now reasonably well understood compared to what scientists knew when the framework was first proposed in 1961. The revolution in exoplanet science has transformed our understanding of these pieces, providing actual data where only speculation existed before. The fourth piece, the fraction of habitable worlds where life actually emerges, marks the transition from astronomy to biology and from relative certainty to profound uncertainty that persists today. We know life emerged on Earth relatively quickly after conditions stabilized. But whether this reflects life being easy to start or reflects survivor bias, the fact that we could only ask this question where life already exists remains impossible to distinguish from our single example. The fifth piece, the fraction of life-bearing worlds that develop intelligence, extends the uncertainty further into evolutionary biology, asking how often the long path from simple cells to thinking minds actually reaches its destination. Intelligence appeared on Earth, but only after billions of years, and whether this represents a common outcome or a rare accident remains unknown and perhaps unknowable from our current vantage point. The sixth piece, the fraction of intelligent species that develop detectable technology, adds another layer of uncertainty involving the specific conditions and evolutionary pressures that might lead toward radio telescopes or their equivalents. Technology requires specific circumstances that we can identify: fire and metallurgy, and systematic science. But how often these align across the diversity of possible worlds and evolutionary histories eludes our attempts at estimation. The seventh piece, how long technological civilizations typically persist, represents perhaps the greatest uncertainty of all, the factor that could dominate the final answer, regardless of what values we assign to everything else. A century or a billion years, the range spans many orders of magnitude, and we have only our own unfinished history to consult when guessing where the typical value might fall. When scientists attempt to combine these factors into estimates, the results vary enormously depending on what assumptions drive the calculation at each step along the chain of reasoning. Optimistic assumptions at each stage compound together to produce estimates of millions of civilizations currently sharing our galaxy, enough that on average they might be separated by only a few light years. Pessimistic assumptions compound in the opposite direction, producing estimates suggesting we might be the only technological civilization in the galaxy, or perhaps in the entire observable universe. An estimate from the 1960s, using the understanding available at that time, suggested perhaps 10,000 civilizations might exist in our galaxy, a number that seemed plausible given what was then known about stars and suspected about planets. Carl Sagan, the famous astronomer and science communicator, sometimes quoted estimates of 1 million civilizations, reflecting optimistic assumptions about the ease of life and intelligence arising given suitable conditions. More recent estimates, informed by better astronomical data, but still limited by fundamental uncertainties about life and intelligence, range from millions on the optimistic end to less than 1 on the pessimistic end, with the pessimistic estimates suggesting we might be alone. The range of responsible estimates spans perhaps 10 orders of magnitude, From roughly 1 million civilizations to roughly 1 in 10 million galaxies hosting a technological civilization, reflecting the depth of our remaining ignorance. The framework does not give a single answer because the inputs are not known with enough precision to constrain the output meaningfully, without making assumptions that reflect the estimator's beliefs more than observed facts. Two scientists using the same framework can reach answers differing by factors of billions, depending on what values they consider reasonable for the biological and sociological factors that dominate the uncertainty. This might seem like a failure, a calculation that produces no definitive result. But the framework's value lies not in giving an answer, but in organizing the question into components that can be investigated separately. Each piece becomes a research program, a set of questions that scientists can approach with observations and experiments that chip away at the uncertainty one factor at a time. The search for life on Mars, the exploration of ocean moons like Europa and Enceladus, the study of exoplanet atmospheres for biosignatures, all connect to the fourth piece, the emergence of life on suitable worlds. These investigations might eventually reveal whether life begins easily, given the right conditions, or whether Earth's living systems represent an extremely rare outcome of chemistry and circumstance. The study of intelligence in other species on Earth, from dolphins to crows to octopuses, connects to the fifth piece, illuminating the conditions under which complex cognition evolves and whether multiple independent paths can lead towards something like minds. Understanding why intelligence evolved here and what conditions favored its development helps constrain estimates of how often it might emerge elsewhere. The ongoing search for signals from other civilizations, the listening programs that scan the skies for artificial patterns in radio waves or other electromagnetic radiation, directly tests whether the product of all these factors yields any companions at all. Decades of searching have produced no confirmed detections, a null result that might indicate low values for some factors, or might simply reflect the difficulty of the search, given the vastness of the cosmos. Each piece of evidence, each new discovery about exoplanets or the chemistry of life, or the evolution of intelligence, or the longevity of human civilization, slightly adjusts the range of reasonable estimates for the corresponding factor. Over decades and centuries, these adjustments might eventually converge on values that narrow the final answer, transforming a framework of organized uncertainty into something approaching genuine knowledge. For now, the framework remains more useful for guiding thought than for providing answers, a structure within which to place new discoveries and a reminder of what remains unknown. The question of whether we are alone in the universe remains open, beautifully and frustratingly open, inviting continued investigation across many fields of science, from astronomy to biology to the study of our own civilization's trajectory. The framework that organizes our thinking about civilizations among the stars has a history of its own, a story of how scientists first attempted to approach this question systematically and break it into pieces that could be examined one by one. This story begins in the early 1960s, when the search for extraterrestrial intelligence was transitioning from science fiction to science, from speculation to a research program with methods and instruments. Frank Drake was a young astronomer working at the National Radio Astronomy Observatory in Green Bank, West Virginia, among the mountains and radio-quiet valleys of the eastern United States. In 1960, he had conducted the first modern search for extraterrestrial signals, pointing a radio telescope at two nearby sun-like stars and listening for patterns that might indicate artificial origin. He called this effort Project Ozma, named after the princess of the fictional land of Oz, a realm populated by strange beings far from normal experience. Project Ozma detected no signals from other civilizations, but it demonstrated that the search was technically feasible and worth pursuing with better instruments and more systematic efforts over longer timeframes. The project attracted attention from other scientists interested in the question, suggesting that a coordinated approach might advance the field more effectively than isolated individual efforts scattered across different institutions. In November of 1961, Drake organized a small conference at Green Bank to bring together scientists from different fields who shared an interest in the question of life beyond Earth. The meeting was sponsored by the National Academy of Sciences, lending institutional credibility to a topic that might otherwise have seemed too speculative for serious scientific consideration at that time. About a dozen scientists attended the three-day meeting, arriving at the observatory nestled in the West Virginia mountains, with notebooks and ideas and questions they hoped to address collectively. The attendees included astronomers, physicists, a biochemist, a neuroscientist, and others whose expertise touched on different aspects of the question being considered. Carl Sagan attended, already developing his talent for science communication, as did Philip Morrison, who had written influential papers on the possibility of interstellar communication. Drake wanted an agenda for the meeting, a structure that would organize discussion and ensure that all relevant topics received attention during the limited time available. The night before the conference began, he sat alone, considering what factors would determine whether interstellar communication was possible and how many partners might exist for such communication across the galaxy. He wrote down a list of factors, each representing a question that needed answering, to estimate how many civilizations might currently be sending signals we could detect with our radio telescopes. The list moved from astronomy through biology to sociology, from star formation through planetary systems, through life and intelligence, to technology and longevity. By multiplying these factors together, one could estimate the number of detectable civilizations, at least in principle. The framework that Drake wrote down that night, which he presented to his colleagues the next morning on a blackboard in the conference room, became the organizing structure for the entire meeting. Each factor prompted discussion among the assembled experts, with astronomers contributing what was known about stars and planets, biologists discussing the origin and evolution of life, and everyone speculating about technology and civilization. The attendees made estimates for each factor based on what was known at the time, though most factors required significant guesswork given the limited evidence available in 1961. No exoplanets had been discovered. The origin of life remained mysterious, and the longevity of technological civilizations could only be imagined based on human history and hopes for the future. The calculation they performed together yielded an estimate of perhaps 10,000 civilizations in our galaxy, a number that seemed both encouraging and sobering. Encouraging because it suggested we might not be alone, that the cosmos might host other minds with whom communication might someday be possible. Sobering because even 10,000 civilizations spread across a galaxy of hundreds of billions of stars meant they were extremely rare and likely very far apart. The meeting marked the beginning of modern scientific SETI, the search for extraterrestrial intelligence, as a coordinated research program rather than isolated individual efforts. The framework Drake presented became known by his name, a tool for thinking about the problem that has remained relevant for more than 60 years, despite enormous advances in our understanding of the cosmos. The attendees of that 1961 meeting gave themselves a whimsical name, calling their group the Order of the Dolphin after a presentation on dolphin communication by one of the attendees, who argued that understanding communication with intelligent species on Earth might inform efforts to communicate with intelligent species elsewhere. The name reflected the informal, exploratory spirit of the gathering. Many of the scientists who attended that meeting went on to influential careers advancing various aspects of the search for extraterrestrial intelligence. Frank Drake continued his work in radio astronomy and SETI for decades, conducting searches and advocating for continued investment in the search. Carl Sagan became the most famous science communicator of his generation, bringing the question of life in the universe to millions through books and television programs. The framework itself became a standard tool in astrobiology and SETI, taught in courses, discussed in textbooks, and used to organize thinking about the question even as estimates for individual factors were revised with new evidence. The discovery of exoplanets transformed the second factor from speculation to observation, while other factors remained as uncertain as they were when first proposed. Green Bank Observatory remains active today, the radio telescope still listening to the cosmos, still occasionally contributing to SETI searches, alongside its other astronomical research. The building where the meeting took place still stands, now part of a larger facility that has grown over the decades since that small gathering in 1961. The 60th anniversary of the meeting was marked in 2021, with retrospectives celebrating how much had been learned and how much remained unknown, despite 6 decades of progress. The framework that emerged from those 3 days of discussion continues to guide thinking about the question, a legacy of that small group of scientists who gathered in the mountains to think systematically about whether humanity might have company in the cosmos. Frank Drake passed away in 2202, at the age of 92, having spent his career advancing the search he helped to formalize and organize. His framework survives him as a tool that generations of scientists have used and will continue to use, a structure for thinking about one of the most profound questions humanity can ask about its place in the universe. The story of that meeting reminds us that great scientific questions are pursued by real people in real places, that frameworks and equations emerge from human curiosity and effort rather than appearing fully formed from abstract thought. The question of extraterrestrial intelligence was taken seriously by serious scientists who devoted their careers to advancing it, giving institutional form to a wonder that humans have felt since first looking up at the stars. The meeting also reminds us how much has changed since 1961, and how much remains the same despite decades of discovery and investigation. The astronomical factors are now constrained by observation. The biological factors remain uncertain, and the question itself remains unanswered. As open today as it was when Drake wrote his list of factors the night before that November meeting, the framework suggests that if its factors have even modestly optimistic values, our galaxy should host thousands, or perhaps millions of technological civilizations spread among its hundreds of billions of stars. Yet we have detected no confirmed signals from other civilizations, despite decades of searching. No unmistakable evidence of technology beyond Earth. No visitors from other worlds documented beyond reasonable doubt. This apparent contradiction between expectation and observation has a name, a tension first clearly articulated by a famous physicist during a casual lunchtime conversation. Enrico Fermi was one of the most accomplished physicists of the 20th century, having made fundamental contributions to nuclear physics and led the team that created the first nuclear reactor in 1942. In 1950, during a lunch at Los Alamos National Laboratory with fellow physicists, the conversation turned to recent reports of unidentified flying objects and the possibility of extraterrestrial visitors to Earth. Fermi, doing quick calculations in his head, as was his habit, noted that if civilizations were at all common in the galaxy, even slow interstellar travel at a fraction of the speed of light would allow a single civilization to spread across the entire galaxy in a few million years. Given that the galaxy is billions of years old, any civilization arising early in galactic history would have had ample time to reach every star system, including our own. "Where is everybody?" Fermi asked, expressing in 4 words a puzzle that has occupied scientists and philosophers ever since. If the galaxy should be populated, if civilizations have had billions of years to arise and spread, why do we see no evidence of their existence anywhere we look? The question has become known as the Fermi paradox, though it was not formally published or developed systematically until later scientists revisited the basic argument and explored its implications more thoroughly. The paradox arises from the apparent conflict between expectations based on the framework and the stark emptiness we actually observe when we look for evidence of other technological civilizations. Several broad categories of explanation have been proposed for why the cosmos appears silent, despite the billions of stars and billions of years of opportunity that should have produced evidence of other minds. Each category makes different assumptions about the values of various factors in the framework, or about the behavior of civilizations once they achieve technology. The first category suggests that technological civilizations are simply extremely rare, far rarer than optimistic estimates from the framework might suggest, with most or all of the biological and sociological factors having values much lower than hoped. Perhaps life rarely arises even on suitable worlds, or perhaps intelligence is an extremely improbable outcome of evolution, or perhaps technological civilizations typically destroy themselves before spreading beyond their home planets. If technological civilizations are rare enough, the current silence would be expected, because there might be no one else to detect within the distance our searches have covered, or within the time our species has been listening. We might be the only technological civilization in the galaxy, or among just a handful separated by tens of thousands of light years, too far apart to detect each other with current instruments. The second category suggests that civilizations exist, but are not detectable for various reasons related to their technology or behavior choices. Perhaps civilizations typically use communication methods we cannot detect, or perhaps they actively hide to avoid risks associated with revealing their existence. Or perhaps they transcend into forms that no longer produce the signatures we search for. An underwater civilization might never develop radio technology, even if highly intelligent and technologically sophisticated by other measures, leaving them invisible to radio searches. A civilization that long ago moved into virtual reality or merged with its computing systems might have no reason to broadcast signals into the physical cosmos anymore. The third category involves the possibility that civilizations exist and are detectable, but that we have not yet searched thoroughly enough to find them, given the vastness of the search space. The galaxy contains hundreds of billions of stars. We have examined only tiny fractions of the radio spectrum, and our searches have been underway for only decades, against timescales of billions of years. Finding a signal might require extraordinary luck, in addition to persistent searching. The right star observed at the right frequency, at the right moment, when an intermittent transmission happens to pass through our solar system. Given the limitations of our searches, the absence of confirmed detection might indicate nothing about the prevalence of civilizations in the galaxy. The fourth category raises the uncomfortable possibility that something typically prevents civilizations from reaching the point where they could be detected, or could survive long enough to be noticed. The Great Filter hypothesis, mentioned earlier, proposes that some step in the progression from non-living matter to galaxy-spanning civilization is extremely difficult, filtering out almost all attempts. If the filter lies behind us, in the origin of life or the evolution of intelligence, then we might be nearly alone in the galaxy, simply because the early steps are extraordinarily improbable. If the filter lies ahead of us, in challenges that technological civilizations typically fail to survive, then the silence might be a warning that our own future is precarious. Some have proposed that civilizations typically destroy themselves through nuclear war, environmental collapse, or other catastrophes enabled by the same technologies that make them detectable, leaving the galaxy populated only by failed experiments and rare survivors. Others suggest that superintelligent artificial intelligence typically replaces or destroys its creators, though whether such AI would itself remain silent is unclear. The dark forest hypothesis suggests a more disturbing possibility, that civilizations remain silent because announcing presence is dangerous in a cosmos where the intentions of strangers cannot be known. In this view, civilizations hide and remain quiet because detection might invite destruction from other civilizations that have learned to eliminate potential threats before they can become dangerous. A more benign version suggests that advanced civilizations might deliberately avoid contact with younger civilizations like humanity, allowing them to develop independently without interference. Much as nature preserves protect wildlife from human contact. The zoo hypothesis proposes that we might be observed but not contacted, protected from knowledge of our cosmic context until we are deemed ready for such revelation. None of these explanations has been confirmed, and the paradox remains unresolved after decades of discussion and investigation. The silence might indicate that we are alone, or that others hide, or that we have not yet looked carefully enough, or that something we do not understand prevents the galaxy from hosting detectable civilizations, despite the apparent abundance of opportunity. The paradox gives urgency to continued searching, because each null result slightly increases confidence that technological civilizations are rare, while each potential detection would transform our understanding of our place in the cosmos. The framework provides a structure for thinking about which factors might resolve the paradox, while the paradox itself motivates continuing research on each factor. The question remains open: And the night sky remains silent as far as we can tell, filled with stars that might or might not host minds, wondering the same things we wonder when we look up at the darkness between those points of light. The framework that has guided our journey tonight offers no final answer to the question of whether we are alone among the stars, but it has given us something valuable nonetheless. It has organized an overwhelming question into pieces. We can examine one by one, transforming mystery into a research program that advances with each new discovery about stars, planets, life, and the conditions that might allow minds to emerge across the cosmos. 6 decades have passed since that small group of scientists gathered in the mountains of West Virginia to think systematically about the possibility of life beyond Earth. In that time, we have discovered thousands of worlds orbiting other stars, found that planets are common throughout the galaxy, and begun to understand which worlds might provide conditions suitable for life as we know it. The astronomical factors have shifted from speculation to observation, with data replacing guesswork for questions about how many stars form, and how many have planets, and how many of those planets might be habitable. These discoveries have generally supported the idea that the galaxy provides abundant real estate for life, with billions of potentially suitable worlds scattered among the spiral arms. The biological factors remain more uncertain, still dependent on our single example of life on Earth, and our incomplete understanding of how chemistry becomes biology in the first place. We search for evidence of life on Mars, plan missions to the ocean moons of Jupiter and Saturn, and develop techniques to analyze the atmospheres of distant exoplanets for signs of biological activity. Each of these investigations might eventually transform our understanding of how common life is in the universe, providing data points beyond Earth that could dramatically narrow the range of estimates for the probability of life emerging on suitable worlds. A single discovery of even microbial life beyond Earth would tell us that life arises independently at least twice in one small corner of one galaxy, suggesting it might arise commonly throughout the cosmos. The factors involving intelligence and technology remain the most speculative, dependent on understanding not just biology, but evolution, cognition, and the social dynamics of species we have never observed. We study intelligence in other species on Earth, trace the evolutionary history of our own minds, and contemplate what conditions might be necessary for technology to emerge from biological intelligence. The final factor, the longevity of technological civilizations, connects the cosmic question to our own choices and the trajectory of human civilization over the coming decades and centuries. How long we survive and remain technologically capable will contribute our data point to the cosmic average, one example among however many the universe has produced. The search for extraterrestrial intelligence continues, with instruments more sensitive than Drake and his colleagues could have imagined when they met in 1961. The Breakthrough Listen project, launched in 2015, represents the most comprehensive SETI program ever undertaken, surveying millions of stars with modern radio and optical telescopes searching for artificial signals. New technologies enable searches that previous generations could not have conducted, including analysis of exoplanet atmospheres for signs of industrial pollution, searches for megastructures that might partially block starlight, and monitoring for transient signals that might indicate deliberate communication or technological activity. The James Webb Space Telescope and future instruments will characterize the atmospheres of Earth-sized exoplanets, potentially detecting signatures of biological or technological activity if they exist at detectable levels on worlds within our observational reach. Each advance in astronomical instrumentation opens new possibilities for discovery. The framework itself remains useful as a thinking tool, a structure within which to place new discoveries and a reminder of what we know, what we suspect, and what remains fundamentally unknown despite decades of investigation. It connects astronomical observations to biological theories to sociological speculations in a chain of reasoning that spans the sciences. Critics have noted that the framework can produce almost any answer depending on the assumptions fed into it, that the uncertainty in later factors swamps whatever precision has been achieved in measuring earlier ones. This criticism is valid, but perhaps misses the point, since the framework's value lies not in producing an answer, but in organizing the question. The question itself, whether we are alone in the universe, connects to deep aspects of human identity and our understanding of our place in the cosmic order. The answer, whatever it turns out to be, would have profound implications for how we think about ourselves and our civilization. If we are alone, or nearly so, then Earth and its living systems represent something extraordinarily precious, a rare or unique flowering of complexity in an otherwise empty cosmos. The responsibility of preserving and extending this precious anomaly would fall entirely on us, the only minds capable of consciously shaping the future of intelligence in the universe. If we are not alone, if the galaxy hosts other minds with whom we might someday communicate or even meet, then our perspective would shift from lonely uniqueness to membership in a cosmic community whose nature we cannot yet imagine. The implications would depend on the nature of those others and the possibilities for interaction across the distances that separate us. For now, we do not know which scenario is correct, and the framework cannot tell us without better values for its most uncertain factors. The question remains open, inviting continued investigation and continued wonder at the mystery that the night sky presents when we consider what might exist among those points of light. The stars continue their ancient patterns above us. The galaxy continues its slow rotation that has been ongoing for billions of years before humans arose, and will continue for billions of years after we are gone or transformed. Whatever the answer to the question, those stars will persist. Those billions of worlds will continue their orbits, and the universe will continue to be whatever it actually is, regardless of our understanding or ignorance. We have done something remarkable in developing this framework, in approaching with scientific methods a question that once belonged only to philosophy and speculation. We have turned wondering into a research program, transformed awe into observation, and built instruments to extend our senses across distances that would have seemed beyond comprehension to previous generations. The framework that Drake wrote down the night before that November meeting more than 60 years ago endures because it captures something essential about how to approach overwhelming questions. Break them into pieces, examine what is known about each piece, identify what remains unknown, and then pursue the unknown through observation and experiment. Whether we find evidence of other civilizations in our lifetimes or our species never makes contact despite searching for millennia, the search itself expresses something fundamental about human curiosity and our desire to understand our place among the stars. We look up at the night sky and wonder, and then we build telescopes to turn wondering into inquiry. The question remains open, beautifully and frustratingly open, an invitation to continued exploration that stretches before us like the night sky itself. Somewhere among those countless stars, the answer exists, whether that answer is countless companions or profound solitude. The framework helps us think about the question. The search, patient and ongoing, might someday help us know the answer. For now, good night from the drowsy astronaut, and I hope to see you again tomorrow.